So this is imageJ software from National Institutes of Health. It's a free image processing and image analysis software. We're going to use it to look at both the size and shape of particles, and in this case I'm going to go through the process to show you how to set things up. Currently I have a color image. Now, a color image is complex. It contains red, green and blue information for every pixel that comprises the image, and I'm only interested in this case in the black material. The black material here is a coal particle that's been immersed in a solvent. You can't see the liquid, but you can see the solvent discolors, and over the period of, I believe, 2 days, what we've done is take an image periodically, let's say every 5 minutes, and you get the transformation from an original particle that's just had solvent added to a significantly swollen coal particle in the solvent. You don't have to worry about solvent swelling theory. I'm more interested in the application of image processing. So I do want you in the theory to go through what an image is and how our various steps transform this image so that we can do analysis. So the first thing I'm going to do is throw away all of the color information by converting it to an 8-bit image. So instead of red, green, blue color image, I'm going to an 8-bit, which is a black and white image, where realistically I've got levels of grayscale. So now my pixel has a value between 1 and 128, and that'll tell me how light or how dark that particular pixel is. Before I go any further and just extract out the particle information, I'm going to go ahead and set the scale. Now, if I move my mouse, actually let me close this for a second. If I move my mouse over the edges of this glass vial, happens to be a test tube, I can see up in here that I go from 179 to 169. Sorry, from 136 to 169. 136 to 169. So on the order of 30 pixels is that distance, and I happen to know that's 1 centimeter. So if I go and go to image and do the scale, I know that in this case oops, I'm sorry, not scale. When I go and image, analyze, set scale, that I know that it's 30 pixels are equivalent to 1 centimeter. And of course I could have calibrated on a scale bar, or if it was a burner, a particular height of the burner, things along those lines. So now I have a scale, so every pixel I know has a length to it, obviously on a height, and I can use that information when I go through the processing to do not only pixel counting to get areas or the cross-sectional area of this particle over time, but I can also do various manipulations to look at size and shape factors as well. So now I have a grayscale image. We have a set calibration. I'm just going to extract out the information I'm interested in. And to do that, I'm going to adjust the threshold. So here we have two sliders. If I go from my 0 to 255 value, I will select everything, and I'm only interested in the coal, so I'm going to adjust this lower value until I only see the coal particle. And in this particular case it's somewhere around the value of 47. This one shouldn't do much, but I'm looking to try and have a nice solid red block without any holes in it. And that's the original coal particle and its transformations over time, and I'm going to go ahead and apply that, and I hit the wrong button, so let me go back again. Somewhere around somewhere around 47, and I'm going to apply, and now I have an image, in which case I've got a particle sequence, and I can see how it's expanding with time. If I go and analyze, I can do various measurements. And if I go and set the measurements, you can decide whether you want to have the area, center of mass, the various shape descriptors, might be useful to have, as well as other shape descriptors that we have over here, such as Fret's diameter, actually, which is a size, not a shape. We can indicate how many decimal places, and we can play with everything else. I'm going to display the label, and I want to also, at this point in time, go and do a labeling so we can see what we're looking at. So I'm going to analyze the, actually I'm going to measure. And when I do that, I have a whole range of structural information that I can utilize. Right now it's everything at once. It's not separated the individual particles. So I'm going to go ahead and do that, and by analyzing the particles. So here I am. I'm going to look at all of them. I'm going to certainly select everything regardless of how round it is, and I am going to calculate that data. I am going to show maybe the outlines. Now when I do that, you'll notice that something quite important has come up, that for some reason imageJ doesn't recognize this as particle 1, and this is 3, 7, 8, 5, 6. So when you go and do a time sequence, you have to go and correct for this. And I don't know why this is the case. It does get better after a little while, but I'm afraid this looks like a manual correction to make sure you've got the data in the right format. But by visualizing it, we can see again the particles and how they're calibrated, and when we do the measurement, and I'm just going to go by masks this time just to show a different look. This is the information that you can then copy and paste into Excel and work up. We have various shape factors, roundness, fret diameter, and in this case it's the area that's particularly important. But remember, again, it's mislabeled the 1 through however many particles we have, and so that has to be corrected. So that's pretty much it. Read the instructions. When it tells you to do a command, it's talking about these commands up here. In the theory, look at shape analysis, shape factors, why it's important, and in the theory also go through and indicate how image analysis is performed, and that you're doing corrections and really selection of the information that's important.